Hello students, welcome to second lecture of mass transfer. Okay, today we're going to discuss the cell mass balances, okay, and some problems, okay, using cell mass balances. Okay, so as discussed earlier, the cell mass balance approach is the same as before, right? So take a thin cell, do a mass rate balance, okay, then derive the flux profile, then put the Fick's law in the flux, and then get the concentration profile. Okay, so the steps are same. Okay, so now you know the combined flux, which is represented by capital N, as discussed in the previous lecture. Capital N means it is the molar flux. So let's solve all the problems in molar flux only. So molar flux units, ignore the mass flux units. So from now onwards, let's use the molar flux units. So capital NAZ. So we are mainly talking about binary diffusion, okay? Only binary diffusion. So we have two species A and B. Okay, I want to calculate the total flux of this species A, right? A, capital NA in the Z direction. For you can write X, Y, or Z, but for simplicity, it is given as Z direction, right? So the mass flux is happening in the direction of Z. Okay, if it is happening in the Y direction, you just simply write Y instead of Z. Okay, so this is given as, the first term was molecular diffusion, that is given by JA, right? That is given by Fick's law. It is nothing but JA Z, molecular flux in the direction of Z of species A, and convective flux. Okay, so it is given as a mole fraction of species A into total, total molar flux, convective molar flux N. But definitely total, total molar flux is a sum of molar flux, convective molar flux of A and convective molar flux of B, okay, in the Z direction. So I will write Z here. Okay, so it is molar fraction of A into total convective molar flux, or the sum of convective molar flux of species A and the B, or you can say net convective flux. Okay, so if you want to calculate for species B, though, you can write the same thing, NBZ equal to minus the total concentration dBA, and I already told you dBA is equal to dAB only, and dou X B by in the direction of Z plus molar fraction of B and total convective flux, that is NAZ plus NBZ. Okay, so this is the definition, so remember this. So XA is nothing but mole fraction. So we can also have homogeneous reaction and heterogeneous reaction. So what happens if there is a reaction is going on? There will be, if the A is reacting to form B and you want to calculate the flux of A, then definitely the A is getting depleted, right? So you have to subtract from the mass conservation equation. And if it is you are doing for B, it is getting produced by the reaction, so you have to add plus. Okay, if it is the reactant, you are doing the balance, calculating the flux for the reactant, then you have to subtract minus consumption or plus consumption, whatever. And if it is getting generated, for as in case of the product, you have to write plus. Okay, and K triple, this is this per unit volume, and this is surface. K double dash means the surface area is taken into account. Okay, so the form is, for cell mass balance, the form is same as before. So in minus out plus generation or consumption. Okay, if you have generation, you have to add plus, and you have consumption, you have to minus consumption rate. Okay, so rate of mass of A in, rate of mass of A out plus production or minus consumption equal to 0, because we are doing at steady state, so it's 0. Okay, so remember this general cell mass balance equation. Okay, based on this only we will solve the problems. Okay, so I will repeat the steps again. Take a thin shell according to the problem. If it is a rectangular slab kind of thing, then you have to take rectangular thin shell of kind of rectangle. And if it is cylindrical, then you have to take a thin shell of cylindrical shape. And if it is a sphere, you have to take a thin shell of spherical shape. Okay, so everything is mass in, but you can also do it in terms of mole. It is the same thing. Also the boundary conditions. Suppose at some point the concentration is given, so that is a boundary condition. Suppose at some point instead of concentration given, the flux is given. Okay, so it is also a boundary condition. And lastly, like in the heat transfer, you applied Newton's law of cooling at the surface. Similarly, using mass transfer coefficient, you can apply this. So suppose here I have a liquid and it is evaporating, and here air is flowing, so definitely the air will take away the vapor, right? So you can use this equation, mass transfer coefficient, to calculate the flux at this point. Okay, and also if there is a, suppose there is a catalyst and it is reacting at this surface, you can also use the surface reaction to calculate the, to find the boundary condition. So let's say some reaction is happening, so you can write Na0 is equal to K, so what is rate constant based on the surface, and Ca0. This is how it is calculated. Okay, let's solve problem. You will get a clear idea. So our first problem is diffusion through a stagnant gas film. Okay, so what is happening is I have a gas A, and here I have, let's say, gas B, mainly the air, and this gas A is diffusing. Definitely it will diffuse because here high concentration of A is here 0 concentration of A. So definitely from high concentration to lower concentration, there will be a mass transfer. Okay, and stagnant gas film. Stagnant gas film means, see, B definitely B should diffuse here as well. Okay, but if the air is flowing in this direction, so it will not have enough time to diffuse in this direction. Okay, the air cannot diffuse in this direction if the air is flowing. Okay, so only the A is diffusing in this direction and B is not diffusing. So this is the case. So air is flowing. So this is called diffusion through a stagnant gas film. The air is stagnant. It will not diffuse in this direction. Okay, only the A will diffuse. So diffusion through a stagnant gas, or also A diffusing in non-diffusing. You can write A diffusing into non-diffusing B. Because the air cannot diffuse because it is moving with high velocity, right? So it will simply move on. It does not have enough time to diffuse here. So you can say non-diffusing B, and A is only diffusing here. So you say A is diffusing, or you can say diffusion through a stagnant gas film. Okay. So this is the problem. So I have a liquid column A. Because of vapor pressure difference, it will evaporate, right? So, and it will try to diffuse to this direction. Okay. And here gas stream is flowing and it will take away this. Okay, so the B, yeah, here it will be A and B, because if there is no if the concentration of A is not 0 here, then definitely it will be a mixture of A and B. Okay, so A and B are moving here, but here there is a high concentration of A, Okay, so mass transfer will take us from this to in this direction. Okay, so you are required to find the profile of the concentration profile of the A, how it will vary with the distance. Okay, so how to take, so this is some kind of tube is there, let's say tube, or it can be of cylindrical shape, or it doesn't matter. In this problem, the surface cross sectional area is given as S. Okay, so only thing is you just consider this thickness. Okay. So you have to take a thin cell, right? So definitely you'll take, since the direction of mass transfer is in this direction, Z. Okay, so the coordinate system is like this, 0 and Z. So mass transfer is happening in this direction, Z direction. So I will take a thin cell normal to this direction. Okay, so this is the thickness delta Z. Okay, what is the volume of this thin cell? S into delta Z, because S, the cross section, so sectional area of this surface is given, right? S. So the volume is S delta Z. Okay. There is no reaction, so there will be no generation or no consumption. Okay. So this is okay. We'll do the balance now, right? So we have taken a thin cell at the distance Z. This point, if my origin is here, so this point distance is Z. Okay, what is this point? If this the shell thickness is delta G, then this point is Z plus delta Z. So what is in point? This is the in point, this is the out point. Okay, and we'll integrate over the whole from Z1 to Z2. Why Z1 to Z2? Because liquid is filled up to this point, and here, because of pressure differences, the liquid will vapor, and this vapor will get transferred in this direction. Okay, so I have to integrate from Z1 to Z2. Okay, first I will do the solvent. So what was that? In minus out plus generation or minus consumption equal to 0, right? At steady state. Okay, you have to write at steady state. Okay, so since Na is nothing but the mass flux, but we are doing the mass rate, right? So we have to multiply with area. So S was the cross-sectional area. So in was what? Mass, we are calculating molar flux of A in the direction of Z at the point Z. This is in, right? What is the out? Area into NAZ at point Z plus delta Z. And there is no generation again, so directly equal to 0, right? We have got this. Okay. Again, rearrange this and take the limits. Okay, if you take the limits, so before that you just rearrange it. So S you can multiply on this right hand side, so you will get only NAZ Z minus NAZ at Z plus delta Z equal to 0. Divide the both sides by delta Z and take the limit from delta Z to tends to 0. You're considering very thin thickness. So what you'll get, since this is the definition of derivative, so definition of derivative is NAZ Z plus delta Z minus NAZ by delta Z is dNAZ by dZ. So you'll have a minus here. Okay, so you'll get this. Okay, now if you integrate this, what you'll get? So NAZ is constant. Okay, so NAZ will get nothing but a constant. Right, so that means NAZ you can write directly NA naught, some constant value. Okay, so this means that the flux is constant throughout all points. Okay, it is not changing. The flux, total flux is not changing with distance in this Z direction. Okay. Okay. Now to get the concentration profile, you have to use Fick's law. Okay. So NaZ, what was the formula for NaZ? You see here. Okay, this was the formula for NaZ. So in this problem, A was diffusing, B was non-diffusing, right? So the flux, convective flux of B is 0. Yes, it is not diffusing in the Z direction. So 0. So you have got only this. So if you rearrange, only X and Z will be there. If put it on this side, you'll get 1 minus XA common, right? So you'll get 1 minus XA into NaZ and the diffusion, molecular diffusion term or molecular flux, right? So you have to shift it on the right side, then you'll get this, right? So you have got this. Okay, so it is saying NBZ is 0 because B is stationary, no convective flux of B. Okay, so if you get this, so you can now put this into here. Okay, you can directly do here also, no problem. Okay, if you put it here, then what you'll get? To do with the now you can see this term. So DAB is constant, right? It's a binary molecular diffusion. DAB is not a function of distance. So you can easily take it out. Again, the total concentration is not a function of distance. It will always be same. So you can take it out and you can shift to the right side and it will become 0, right? So finally you'll get this. Okay. Now you take the first integration. So if you take the first integration, you'll get this C1. Okay. Then again take the second integration. And you'll get this one. Right. Now so C1 is a constant, right? It can be anything. So just replace C1 for simplification. It will make the simplification easier if you use C1 in terms of ln, right? So I can write ln K1 instead of C1 and I can write ln K2. Okay. So if is this one, then you can again rewrite this like this. Okay. Now you have to use boundary conditions to calculate the constants K1 and K2. Okay. So you already know at Z equal to Z1, at this point, what was the concentration? Molar fraction X1, right? What is the molar fraction at this Z2? This is X2. I mean, I have to write XA2 because it's a molar fraction of 1 and 2. Yeah, a molar fraction of A at 0.1 and 2. Right? So if you put that, this is the boundary condition. If you put the both boundary condition, you will easily get the constants K1 and K2. So if you rearrange, you will get this form. Okay. So this is the profile. And if you want to write in terms of, you want to calculate the molar fraction distribution or concentration profile of the species B, then you have to just use this. You know, total mole fraction is always 1. So XA plus XB is equal to 1 at 0.1. So XA1 plus XB1 will be 1. Total mole fraction will be 1. At 0.2, XA2 plus XB2 will be 1. If you use these relations and put it here, you can also find out the profile for B. Okay. So this is how you find the profile. Also, what is the mole fraction? Since it was a liquid, at this point, what will be the mole fraction? So we generally calculate like vapor pressure. What is the total pressure? P. And what is the vapor pressure of the liquid A at this point? So PA. So XA can be calculated like this. And if you find out the vapor pressure at this point, that is, you'll get the mole fraction at 0.1 for A is like vapor pressure of A at 1.1 and divided by total pressure. Again at 0.2 you can calculate the mole fraction by vapor pressure of A at 0.2 by total pressure. Okay, so this is how you calculate the mole fraction. So you have got the profile. So if you try to plot this equation, so for A, so A is in this direction, this is the Z direction. So from 0 to 1, so you will get this. So x1 is highest at this point, Z1, and it is diffusing to a lesser point, lesser concentration, this point, xa2. Similarly, this is for B. Okay, because if the xa is 1, then xb is 0, right? Xb, the concentration of B was highest here and 0 here. So it is like this. This is how you use the shell mass balance to calculate the concentration profile. Okay, you can calculate the average velocity like this. Okay, so one more thing, logarithmic mean. What do you mean by logarithmic mean? So suppose I want to logarithmic mean. So it is basically like this, like two quantities, like like let's say I calculate the log mean area of areas. So A2 minus A1 ln A2 by A1. This is your A log mean. This is called A log mean. Similarly, if you say XB is the log mean, logarithmic mean average, then XB2 minus XB1 ln XB2 by XB1. Okay, let's discuss the second problem. It is not given in this book, but you have already studied that in the mass transfer course. So what if there is no stagnant gas film? So the gas B will also diffuse in this direction. It is not flowing in this direction, but it is diffusing in this direction. A will diffuse in this direction and B will diffuse in this direction, because there is high concentration of B and there is low B concentration. So it will diffuse in this direction, and here high A concentration and here lower. So A will diffuse in direction. So this is the case of like equimolar counter diffusion. So equimolar counter diffusion means the molar flux of A and B are same, and they are counter diffusion, though they are in opposite directions. A is diffusing in this direction, sorry, B is diffusing in direction, A is diffusing in this direction. So they both are diffusing in opposite directions, and the flux values are same. Okay, so with same equimolar concentration or equimolar flux. So what will be the concentration profile or molar fraction profiles if this is the case? Okay, so we have to approach this problem in the same way. We take a thin cell like before. Okay, only the difference is this will change. The definition of the combined flux will change. So this was the formula for the combined flux. Now, see this equimolar, right? So equimolar means NAZ is equal to NBZ, right? But counter diffusion, opposite direction, so minus. Okay, because in that problem we took Z, positive Z in this direction, so NZ is positive, but B is diffusing in this direction, so it has to be negative. So negative. So if this is true, then this term will become 0, right? Yeah, this term will become 0. So only you are left with this. So simply put this in that equation. So we'll go again once. So this term will not be here, okay, in the equimolar counter diffusion. So NZ is simply minus C dAB dXA by dZ. Okay, so take a thin cell, already taken a thin cell. Okay, do the in out balance. There is no generation or consumption, so simply this. Okay, take the limits delta z tends to 0, you get this derivative. Okay, just simply put the definition of NAZ. This will not be here. Okay, so CDB is constant, just divide on the right hand side, so you will get this. So this will not be here, so you will get d square xa by dz square equal to 0. This is the equation for equimolar counter diffusion. Just integrate twice. So if you integrate it, what you will get? So after first integration, you will get dxa by dz equal to c1, right? Do a second integration, you will get xa is equal to c1z plus c2, right? So you have got xa equal to c1z plus c2. Now use the boundary conditions. So at at z equal to z1, xy equal to xa1, same as before. At z equal to z2, xa is equal to xa2. So you'll get, put the first boundary condition here. You'll get xa equal to c1 z1 plus c2. Second, you'll get xa2 c1 z2 plus c2. Solve for c1 and c2. What do you get? So first subtract it. This is equation 1 and equation 2. First do 1 minus 2. You get xa1 minus xa2 equal to c1 z1 minus z2. Okay. So you have got the value of c1. c1 is nothing but xa1 minus xa2 by z1 minus z2, right? So you put the value of c1 in any of the equation, you will get the value of c2. So c2 will be xa1 minus c1 into z1, right? So xa1 xa2 by z1 minus z2 into z1. So if you put these values here, c1 and c2 here, what you will get? So xa will become c1. What is c1? xa1 minus xa2 by z1 minus z2 into z, right? Plus xa1 minus xa1 minus xa2 by z1 minus z2 into z1. Okay, so if you, these terms are common, right? So if you take common, so this is z1. So if you take out this common, what you'll get? xa1 minus xa2 by z1 minus z2 into Z minus Z1, right? Plus XA1. So this is the XA. You can see this is the linear profile, right? It will change linearly. So as you increase the height, it will increase. So this is the slope, right? And this is the intercept. So how will the profile look for this problem? So for this, it will be something like linear, a straight line like this. And for B, it will be like this. Okay, instead of this curve. Okay. So this is how you solve the problem using cell mass balances. Okay, let's discuss the last problem, diffusion with a homogeneous chemical reaction. So we have this beaker, okay, here it is liquid B and here it is a gas. So gas will diffuse in the liquid B, okay. So here all the gas, so gas will try to diffuse at this point, okay, and it will react with B, okay. So how will you do the shell mass balance? Okay, same as before. So first know the bounding conditions. So this, since our main species is A, so it is taking the origin at this, you know, and this is your Z direction. So this is your Z equal to 0 point, and this is Z equal to L point. Okay. So how the concentration will vary within the liquid B? Yeah, let's find out. So basically, this is absorption of A by B with some kind of reaction. Okay, so we have A plus B into AB. So this is, it is assumed that this is, you know, first order homogeneous reaction. So B is in bulk, so the concentration B is constant. So we assume that this is first order reaction. So the rate of reaction will be RA triple dash, because based on the volume. So it will be minus K1 triple dash Ca. Okay, this is the rate of reaction. So this is pseudo first order reaction. As you can see, the molecularity is 2, but the concentration of B is in high. Okay, so you can assume it is Cb naught, that is constant. So the rate of reaction should have been Ca Cb, but concentration of B is very high. It's constant, Cb naught. So you can ignore this. So it is only a first order reaction. Okay. So as before, take a thin cell balance. Okay, the cross-sectional area is given as S. So delta Z of thin cell balance. So the in point will be down here at Z equal to Z, and out point will be here. And within this volume, there will be a reaction. Okay. So since A is reacting, that means it is a consumption, right? So you have to have minus here. It is not a product, so it is not getting generated. So if it is a product, then it should have, you should put plus, but if it is a reaction, you should put minus. Okay. So the thin cell balance is there. So in minus out plus consumption. Consumption is all itself a minus. Okay. Equal to 0. So what is the in? Area into the mass flux. So NaZ, right? Species A in Z direction at what point? Z point. Minus out S into NaZ at Z plus delta Z. And remember, this is minus K1 says per unit volume. So what is the volume of this shell? That is S into delta Z. So you have to multiply with S into delta Z with this to get the mass rate, because this rate of reaction will be, if you're doing molar flux, so mole per unit volume per second. Okay, so you have to multiply volume to get mole per second. Okay, because you have multiplied area with the molar flux, you will get mole per second. So this has to be mole per second. So you have to multiply with the volume. So this is the volume, because S is the cross-sectional area. Okay, so if you put here, so you'll get this equation. So first divide both sides with S delta Z. Okay, so if you divide, so S cancels out here, only delta Z will remain. Okay, and here will be K1C and 0. Now if you take the limit delta Z tends to 0, you'll get dNA Z by dZ. So it should have got this, but if you shift to the right hand side, you'll get plus plus only. Okay, so this is the first order differential equation. Now you have to solve. Before solving, you have to put the, you have put the definition of NAZ. Now you can see that A is diffusing, right? Okay, and so you can also say that B is also diffusing in A, because if A is diffusing by relative motion, B is also diffusing in A. Okay, so you have to use this equation from the earlier definition of NAZ, because you can see if NAZ is diffusing, then because of relative motion, B is also diffusing. So this term will become 0. Okay, so only you're left with this. Okay, so you have to consider only this part. So this is nothing but, if you multiply the consideration to CA, so XA into CA is nothing, is nothing but CA. So you'll get NAZ equal to DAB minus DAB into do CA by do Z, right? Okay, this is what you have got. Okay, now you put this in this instead of NAZ, so you'll get this. Okay, so this is now second order differential equation. So before solving this, let's make this in the form of this. So I will try to make this equation in this form so that the solution is direct, right? So to make this equation in this form, in that form, so we have to divide by DAB, right? So I will make it dimensionless. Okay, so if we multiply by L square and divided by CA naught by DAB, so what will become? CA by CA naught will become dimensionless, right? And DAB will cancel out. Here it will come here. So you'll get something like this. So this is your gamma, capital gamma. This is zeta, right? So the Z by L is dimensionless. CA by CA naught is the gamma, dimensionless, right? And what is phi square? If you collect the terms, you'll get, see, gamma is this, it is Z by L, and phi square is K triple dash 1 L square by DAB. Okay. You might ask why you have divided by or multiplied by L square, because there you have dz square. Okay, z square. So you need L square to make it dimensionless, right? To make it zeta square. Okay. So this is the form. So now this is the same form as this one. Okay. So what will be the solution? So y will become equal to C1 is a constant. So cos hyperbolic A x, right? This x plus C2 sine hyperbolic A into x, right? So what will be the solution of this? So gamma will be equal to C1 cos hyperbolic A. A means phi. Phi x means zeta, right? Plus C2 sine hyperbolic phi zeta. Right? This is the solution. Just you have to apply the boundary conditions to get the final solution. So what is the boundary condition? This was your original boundary condition, right? So you have to change these boundaries in terms of the zeta and gamma. So at z equal to 0, what is zeta? Zeta is nothing but z by L, right? So 0 by L. So zeta is also 0. So CA is C naught. So what is your gamma? Gamma is nothing but CA by CA naught, right? So CA is CA naught. So 1. So this is the boundary condition. First, gamma equal to 1. At zeta is equal to 0, gamma is equal to 1. Consider second one. So what is the definition of zeta? Z by L, right? So Z is L. L by L is 1. So at zeta equal to 1, or dCA by dz equal to 0, or NAZ by equal to 0, this is flux is 0. So write dCA by dz. So divide on both sides by CA naught. L by CA naught, right? So you'll get d gamma by d zeta equal to 0. So you can use this to find the C1 and C2. Okay, so finally you'll get this equation. Now just re-put. So gamma was nothing but CA by CA naught. What was phi? Phi was this. What is zeta? Z by L. And again cos H. What was phi? This one. So this is your concentration profile of A. Okay. So with this, we complete all the transfers, momentum transfer, heat transfer, and mass transfer. So from tomorrow onwards, I will discuss the question papers. Okay. Thank you.